let me start with how I met with Tamás. And in my family, the Roska name was known because my mother and Marietta and my mother were friends. So they knew each other. Sometimes we met, but when I really met to Tamás, it was in 1990 when a professor of digital circuit at the Technical University of Budapest recommended me to visit a class or to take a class about neural computing, which was really not known at that time. And when he told that it is delivered by Tamás Roska, I immediately decided to take it. So I went to his spring class. I learned about many things, including John Hopfield, who got the Nobel Prize this year, and then I joined to his laboratory in the fall. He gave me, this was the time when cellular neural network was introduced, and he gave me the first, or one of the first publication, Professor Chora's publication of cellular neural network theory and architecture and application. I spent a few weeks with it to understand everything, and I could attend the first CNNA conference. So let me say a few words what we did in the laboratory in the 90s. Tamás invented the CNN universal machine, and it was a great and very surprising invention looking back from now to it, because it was an analog, cellular neural network was an analog computer, and he made a digital microprocessor out of it. And it was really remarkable, really interesting thinking architecturally about it. We worked about the biological motivation, the receptive field atlas, and CNN models, and Professor Peter Szolgai already mentioned the CNN emulator board. I was involved in the software of that, and I was involved, or I led actually the CNN chip development system design. And obviously there were many other things. I'm just mentioning a few things what I was involved mainly. And this was the research team in the 2000, and you can see some faces, our dean and Kristóf Karacs. Peter Szolgai is here in the first row, and Csaba Ekecki in the center, and other people as well. And of course, Tamás is in the first row with the book which was just appeared. Anyway, this slide already, this picture was already shown by Peter. So these were the cellular neural network chips which appeared, and actually this was, according to my consideration, this was the essence, because there were lots of theoretical results, there were many things, but I am an electrical engineer and a computer engineer, and I appreciated mostly the chips, and I appreciated the processing power, the efficiency of these chips, and these are the chips. Peter was already talking about it. I really programmed most of those and understood those deeply. But at the same time, it turned out that the analog implementations were not accurate enough, though I'm still not sure why industry didn't take it, because we put lots of effort to put it to introduce industrial applications, and the industry was somewhat conservative, or maybe we didn't find the killer application. This was Tamás' words, to find the killer application and reach the industry. They didn't want to learn the new technology, and at the time the VLSI technologies is forwarding nowadays as well. But at the time, deep submicron and very deep submicron technology supported only the advances of digital chips rather than analog chips. So after a while, analog chips were not profiting from the scaling down, and when GPUs appeared, they started to rule and they took over it. But people may ask, okay, but what did we learn from it? And these are the interesting questions. And now I am teaching the basics of the convolutional neural networks at the faculty. And when I'm teaching it, I notice, yes, we were thinking about it in the 90s. Yes, this is really resembling what we did at that time. So what are these things? First of all, the convolutional approach. Well, it's sort of trivial. The convolutional approach was already used by classic image processing. So in many feature extraction and pre-processing, it was used. But cellular neural networks were the first where practically only convolutional approach was used for feature extraction. And actually now convolutional neural network use it the same way, only these. Okay. On the other hand, as I said, Tamás proposed the cellular neural CNN universal machine, so the microprocessor, and in the microprocessor the convolutional operators were sequentially implemented, one at a time. Now it is neuron by multiplication at a time. At that time it was one feature map or one matrix at a time. But we didn't use so many layers, and on the other hand, what we couldn't solve, or what we solved but not in this way, since our chips were rather rigid, they couldn't change the size of the image, or there were some approaches but they couldn't efficiently change the size. We had to keep the size and played with tricky things like patch logic or things like that. While nowadays convolutional neural networks can simply reduce the kernel size and combining distant features. On the other hand, the dynamic layers, what András already mentioned, and which is really unused nowadays. And these dynamic layers are still much, so these dynamic layers, the analog dynamics, analog array dynamics, can be much faster. They can be used for wave computing, they can be used for diffusion or decisions, and these are not really efficient. I mean, this cannot be implemented directly or easily in digital domain, so this is why they are not used. The big difference was the template design. At that time, we said that we would like to understand what's going on in the different features. So let's apply an edge extraction, let's apply a corner extraction, let's find the edges or find the dark areas or the bright areas. We wanted to understand it. And this is exactly the opposite what convolutional neural networks does nowadays. Because they do it on a data-driven way. They collect thousands or millions of images or data and train it, and we have no idea what the features are doing. And actually, the last thing is the biological motivation, what I wanted to say. The biological motivation, we learned a lot. We actually, Tamás' idea was to cooperate with neurobiologists in Budapest, in Berkeley, and different places, and we learned how to use local adaptation, how to use different kind of things, and how to implement different retinal circuits. And actually, in these retinal circuits, they are also maps, feature maps, but we have no name for it, because we cannot explain what's going on it. I mean, what is the reason? We can describe it mathematically, like the feature maps, but we have no idea why it is good. And this is quite similar to convolutional neural network. My last part is the template size consideration. Both of the approaches, I mean the cellular neural networks, though we were talking about larger kernels like 5x5 or 7x7, but once we were talking about implementation, immediately turned out that only 3x3 is possible. And similarly, convolutional neural networks started to use large networks, and later on they figured out that small networks or small kernels are efficient. Okay, and I started how I met with Tamás and what I'm doing now. So I work, my main workplace is at Stocky, and I showed this photo about our group in 2000. And now I'm the head of this group. And after Tamás passed away, we discussed with Ádám Csurgai and Ákos Zarándy, and somehow we were discussing how to proceed. And Ákos told me that Tamás would like you to go on with this laboratory and keep it alive. And some people are still there, not too many because people are coming and going, but the spirit of Tamás is still there. And this is what I am doing now, to keep it. Thank you for your attention.